my classes on fundamentals of electrical circuits, and today we go into the last section in this first module of electrical circuits. And the last section is with respect to the two-port networks. The two-port networks have a lot of concepts entered within. Like for instance, it is just a representation. It's not a full circuit. So you can give your own interpretations to that. At the same time, the parameters are constants, which are describing the insides of a system. And the variables happen to be what you can observe from the outside. So you also have another understanding with respect to the two-port networks, in the sense that they are essentially a result of certain sources being given and measurements being taken. Okay, so the first slide that is put here on the right side will give different interpretations to two-port networks. Okay, of course, we have a black box there, right in the middle. And what do black boxes generally represent? They represent something which is complex, and perhaps we don't know what is all inside it. So what we do is that we look at it from two different sides. One is where we give the source. Okay, so let's say that we are giving the source V1. Okay, of course, it's an electrical circuit, so the best way to understand electrical circuit is to give a source. And so it draws a current. Both these are measurable. So when you are having measurable quantities, you have an idea as to what is what. And then there is a pair of terminals of interest to us, let's say, and that happens to be terminal 2. Okay, so at port 2. At port 2, you can again use instruments, and you can measure V2 as also the current I2. Of course, certain directions are taken as convention, such that you can describe the different kinds of parameters that are there. The most natural kind of parameters to me looks like the Z parameters. So the Z parameters have, again, as I said earlier, some constants. They are named as Z11, Z12, Z21, and Z22. Similarly for all parameters. So in this section or in this session, we'll be looking at both Z parameters as also Y parameters. We will also go into H parameters and A parameters in the subsequent sessions. And there are other parameters as well, or there are other representations as well, but there are some of them are just adaptations or some kind of convoluted understanding of whatever we will be discussing in our sessions on two-port networks. Another important idea that I would like to convey to you happens to be that now we have the parameters representing something else. They are telling us about what is happening inside. Okay, or in other words, there are different extensions to this particular approach in all kinds of ways in which we can understand electrical engineering. Like for instance, the signals and systems. The signals are on the outside, the system is the black box inside, and so that's one approach. And others, of course, even in control theory, okay, the bulk manner of understanding control theory happens to be that it's given by X dot. The representation is again given by X dot is equal to AX plus BU. So U is the input. Of course, there's an output quantity as well, but let's just talk about A. What is A? A is essentially talking about this black box in which all the resistors, inductors, capacitors, diodes, etc., all happen to give rise to whatever we want the system to do, and that happens to be measured at port number 2. So this is the general understanding, and of course, each of these parameters you can measure as is shown on the left-hand side. But as we do the problems, we try to understand whether we need this kind of understanding at all. The third perspective that I would like to pass on to you with respect to two-port networks happens to be that it also gives the nature of the circuit. Like for instance, that the parameters tell us the nature of the circuit. Like for instance, for a two-port network, these are questions as well. For a two-port network, if it is reciprocal, what do you mean by reciprocal? You give something, you get something, you give the same thing on the other port, you get something, you get the same thing that you got on port 2 on port 1. So if it is reciprocal, for H parameters, H12 is equal to minus H21. Similarly, for symmetrical networks, okay, you look at it from this side, you look at it from the other side, there is symmetry. In that case, for H parameters, it happens to be H11, H22 minus H12, H21 is equal to 1. Similarly, for reciprocal networks, both for Z parameters as also for Y parameters, Z12 is equal to Z21 or Y12 is equal to Y21. Then we move on to the ABCD networks or A parameters. In A parameters, the reciprocal networks requires that AD minus BC equal to 1. Okay, where A, B, C, D occupy the same kind of spaces as Z11, Z12, Z21, and Z22. Okay, so that's one thing. And for symmetrical networks, A should be equal to D. Okay, so the nature of the circuit is essentially put in this slide. And in many years, several questions of these areas have come. Okay, so all these problems are addressed at one go. Okay, just as explanatory to the nature of two-port networks. So let's move into the first problem. Okay, so here I have used the most important remembrance that we might need if we are answering exams like GATE examinations, such that V1, the source that you have given, or the voltage that we are connected, voltage source that we are connected to port 1 is the same as equal to Z11 I1 plus Z12 I2, where I1 and I2 happen to be the I1 happens to be, both happen to be the consequences of application of voltage V1. Similarly, V2, which we measure on port 2, let's say, okay, of course, we can apply it on port 2 as well, because if they are reciprocal, then same thing happens. Then it's the same as equal to Z21 I1 plus Z22 I2. Okay, so based on this, let's see how we can do the first problem. The two-port network P shown in the figure has ports 1 and 2 denoted by terminals A, B, C, D. Okay, respectively. It has an impedance matrix Z with parameters denoted by Z, I, J. A 1 ohm resistor is connected in series with the network, okay, at port 1 as shown in the figure. So it is already shown. The impedance matrix of the modified two-port network shown as below, which is the one. Okay. So we should realize that there is another way of interpreting the circuit which has been represented using Z parameters. You can use what is called as the T network, okay, which we also call as the star network. So what does the star have? It has what is called as Z1 on the input side, Z2 on the output side, and Z3 in the middle. And so what is Z11? It is the same as equal to, if you look at what we had put in the earlier slide, it is the same as equal to V1 by I1, where I2 is equal to 0. Okay, so how do you do? So then it's very clear that V1 is applicable across the voltages, across the impedances Z1 and Z2. So Z1 plus Z2 gives us Z11. Similarly, Z2 plus Z3 gives us Z22. And what is in between, which is equal to Z12, will give us what is called as Z11 as Z12 as also Z21. That is, Z3 will be the same. Okay? So if we add 1 ohm resistor to the input side, it affects only Z11, because Z11 will be given by Z1 plus Z3, and now this 1 ohm will also come into the picture. So if you, from all the 4 answers, we can pick out C, because only there we see that the slot or the box given for Z11 is now changed to Z11 plus 1 because of the 1 ohm resistor which has been added. Okay. So this interpretation has just come, I hope has come suddenly to you, in the sense that we can always reinvent, or we can give it another hue, and another hue that we are giving is that we are considering the unknowns within that black box as a T network. Okay, and the T network or the star network, we have Z1, Z2 and Z3 in the middle, such that Z1 plus Z3 gives us Z11. Similarly, Z2 plus Z3 gives us Z22. And what is in between is going to be both Z12 as also Z. And it is both. It is a reciprocal circuit, and it can be symmetrical if all the values have equal values. Okay. So let's move on to the second problem. Okay. What is it? For the two-port, okay, of course, we are shown Z1 and Z2 only. Okay, so what we earlier called as the impedance in port 1, okay, exclusively in port 1, which is not shared by port 2, is absent, or the impedance is equal to 0. Okay, so obviously, if the impedance parameters are asked, as can be seen in the answers, it's going to be 0 plus Z1 as going to be the Z11 quantity. Okay, and Z22 will be, of course, Z2 plus Z1, and Z12 and Z21 are going to be the same and is equal to Z1. Okay, so of the 4 answers chosen, and according to the question asked for the two-port network shown in figure, the Z matrix is given by, again, 0 plus Z1. Okay, so Z1 is there in all answers. Then Z1 plus Z2, that's going to be there, okay, only in C and D. And then both Z1 2 as also Z21 is going to be, Z1 is given only in D. Okay, so very easily you can choose D. Okay, moving on to another interpretation. The Z matrix of a two-port network is given as 0.9, 0.2, 0.2, 0.6. The element Y22 of the corresponding Y matrix of the same network is given by. Okay, since Z parameters and Y parameters are duals with respect to each other. Why? Because the representation is as shown below in this slide. There is I1 is equal to Y11 V1 plus Y12 V2. And I2 is equal to Y21 V1 plus Y22 V2. What does it tell us? It tells us that V multiplied by V inverse will give you Y11, Y12, Y21, Y22. And what is Y inverse? Y inverse is the same as equal to Z, or Z inverse is equal to Y. Okay, so if you have a matrix, if you want to get if you have a matrix representing Z, you can get Y by just simply taking the inverse. Okay, and if we require only Y22, it's very easy to see that, or a 2 by 2 matrix. That's another advantage of working with two-port networks. It will always give you the inverse very easily. Why? Because first and foremost, you will take the determinant, and what's the determinant? 0.9 into 0.6, that is 0.54 minus 0.54 minus 0.04. Okay, so that's equal to 0.5, and so it's and that's going to be on the denominator. So 0.5 is on the denominator. You have to multiply by 2 all the elements, and we require only Y22. So what do you do that for that? You just interchange or exchange between 0.9 and 0.6. So now we are going to have 0.9. Okay, and 0.9 has to be multiplied by 2. Okay, about other content, I suppose you are very clear what is what. Okay, so we move to the fourth problem. Okay, so a two-port device is defined by the following pair of equations. So here I1 is given. I1 is given as 2V1 plus V2. And I2 is given as V1 plus V2. Immediately we see Y parameters there. And so we fill up the box with Y as equal to 2 from the first, and 1. The first row is filled from the first equation. The second row is filled from the second equation. So 2, 1, 1, 1. And what is asked is its impedance parameters, all the impedance parameters. So again, we go back to our recent understanding of taking its inverse. Okay, we get Z. Okay, so how do you invert? First and foremost, 2 on the 2 minus 1, so 1. So denominator is going to be 1, and then 1 and 2 are going to be exchanged. Okay, so you will have 1 and 2. That is the diagonal elements. The others will get a negative sign. Okay, and then you simply divide by, because and you don't have to divide by 1. You get whatever you get. You are going to put you are going to express them as it is. So what do we have? You have 1. Okay, then it's going to be minus 1. Then it's going to be again minus 1. Okay, that is the third element. And finally, we are going to have 2. Okay, so B seems to be the best option. Okay, and the only option, of course. So moving on to the sixth problem. Yeah, so we are moving quickly because there are plenty of problems in this area. Okay, so we have, for the two-port network shown the figure, impedance Z matrices. Okay, so we are being given what is called as a pi network. Okay, so pi network you can convert into a T network or a star network, and you can easily do, and then you can go with Z1 plus Z2 as Z11, Z2 plus Z3 as, okay, so whatever you call as Z1, Z2 and Z3. Okay, so I'm just talking randomly, and then of course whatever is in between you can call it as equal to Z12 and Z1. Okay, so what do we have here? We have found out the star equivalent by simply multiplying 10 into 30 divided by 10 plus 30 plus 60. So we are having 3, 18 and 6 as the components in the legs of the star. Okay, so now it's easy to find that Z11 is equal to 3 plus 6, 9. Z22 is the same as equal to 18 plus 6, 24. Okay, and what is common is going to be Z12, Z21, and that's equal to the common element, which is 6. Okay, so C seems to be right. Okay. Yeah, so now if we are having a pi, then it actually, if a T suits or T can represent the Z parameters, then a pi will represent the of course, when you're talking about pi, you have to think in terms of admittance again. Okay, so if impedances in a star represents Z parameters, then admittances in a delta or pi will represent the Y parameters. Okay, everywhere the duality comes into the picture. Okay, so what do we have here? Yeah, so how do you find out the parameters? Okay, from a pi network. Okay, again, just a small picture is given because y11 will now be the same is equal to y11 plus y12. Okay, as to y11, since y11 happens to be the first leg. Okay, between the terminals of port 1. Okay, and y22 will be if y. So if we so a pi network with its admittances is given here, where we see that y1 plus y2 will give you y11, y3 plus y2 will give you y22, and y3 will give you, and minus y3 will give you the y12 as also y21. Okay, so let's look at what we have here. We are given in the 7th problem, we are given a pi network. Okay, so what about the pi network? So we are given impedances or resistances. So immediately what you do is that you try to go for the admittance values. Okay, because you can use it directly, since the question happens to be that you have to find out the short circuit admittance parameters. Why are they called as short circuit? Because you are short circuiting the voltage, or you're putting the voltage is equal to 0, or short circuiting to find out the parameters. Okay, so short circuit admittance parameters will be given from the admittance value. Okay, so how do you obtain the admittance? By simply finding the reciprocal. So 2 happens to be common as the admittance value of all the resistances. Okay, so now we have 2 plus 2 4, and we have 2 plus 2 4 both for y11 as also y12. Okay, and then minus 2 will be the quantity in the which is going to be common with respect to y12 as also y2. Okay, it's very simple, but certain conventions need to be thoroughly understood and remembered. Okay, so in this problem, that is in 8th and 9th, we go for a different kind of structure, and we use the understanding that we have with respect to the fact that V1, if it is impedance parameter, it's going to be V1 is equal to Z11 I1 plus Z12 I2, and V2 is the same as equal to Z21 I1 plus Z22 I2. Okay, so let's see. So we have input port, and then we have output port. So in between the input port, on the upper arm we have 3 ohms, and in the lower arm we have 6 ohms, and they are cross coupled. Okay, so let's see what we are expected to do. We have to find out the Z parameters for the 2-port network shown. Okay, so I hope we remember the equations wherein it's understood that V1 by I1 will give you Z11 so long as I2 is equal to 0, or in other words, the other port is not given any current. Okay, not given any current, it doesn't talk about anything with respect to voltage. Don't talk about voltage at all. Okay, so we see that. So let's give a voltage on port 1 and allow a current to flow. What will happen to the current? Okay, so current will, again, okay, if you look from the first port, it's very clear that the current is going to split. Okay, it's going to split between the 3 ohms because it can return back through the cross coupling. Similarly, through the cross coupling, the other cross coupling, it will go to 6 ohms and return. Since it's this provision for return, the current splits into 2. One is 3 ohms, one is through the 3 ohms, the other part is through the 6 ohms. And of course, the ratio is going to be, in the 3 ohms is going to be 6 by 9, and in the 6 ohms is going to be 3 by 9. Okay, whatever is going to come, 3 by 9 of the current. Okay. Okay, so now we can find out what is called as what is the input port. Okay, so input port, if you want to find out V1, it's going to be the voltage across 3 and 6 ohms, which are now connected in parallel. Okay, so 3 and 6 in parallel is 3 into 2 by 3 or 2 ohms. Okay, so Z11 is equal to 2. Okay, similarly, the same situation prevails if you look from the other port as well. Again, 3 and 6 are in parallel. Okay, and now you are injecting I2, or you are connecting V2 and injecting I2. Still the same situation is there, so you will get it as equal to 2. Okay, and now we let us look at what is common between the two. Okay, so when you look at what is common between the two, okay, you can see that again we are having a parallel combination, and when you are having a parallel combination, this also comes in between. So again, it's going to be -2. Okay, so if you can visualize the parallel effect of the two resistors, then it's very easy to see that you can see that all values are going to be 2, 2, 2, 2. But of course, it's going to be -2. Why is Z12 and Z21 minus? Because the sense of measuring the voltage happens to be different. Okay, that's what is shown here. So now moving on to the ninth problem, a similar situation is shown here. But the only difference happens to be that in the cross coupling, we again have impedances. Okay. So what do we have here? We see that we have ZA is equal to J2, ZB is equal to J2, and we have, we already talked about the cross coupling, the values of the open circuit impedance parameters. Okay, so we again want the impedance parameters from the lattice circuit that's given. Okay, so again back to we can easily find out the two the Z11 and Z12 because they look the same. Okay, and what is what? Let's say we are applying V1 and the current splits into two. It flows through ZA, okay, and then ZB and comes back. Okay, similarly it flows through ZB and then ZA and comes back. If you are looking from port 1, from port 2 you see a similar picture. You inject a current I1. What happens to it? Okay, of course, by supplying voltage V2 there, then it again splits into ZB and ZA and then comes back. Again, that's one splitting, one circuit. The other circuit is ZA and ZB. Okay, so what is ZA plus ZB? Because they are happening together. So ZA plus ZB is 2 plus J2. Okay, and then they are going to be in parallel, as was mentioned earlier. If you look at V1 from port 1, or if you look for V2 from port 2, by virtue of the current splitting and coming together, we see that it's going to be a parallel combination of impedances. So that's equal to 2 plus J2, and when they are in parallel, 2 plus J2 by 2 because they are in parallel. So 1 plus J has to be both Z11 as also Z12. Okay, so just as we saw, so if this is the situation, then let us pick up. Okay, earlier we just simply said that -2 -2. In this case, let's see how we can find out Z12. Okay, so what is Z12? Okay, which is going to be the same as equal to Z21 because of the symmetry. Okay, so what is going to be Z12? Okay, Z12 is going to be current I2 being injected. Okay, and V1 being washed. So let's say I2 has come in, okay, as can be seen by the arrow, and it creates a voltage across ZB, okay, and then it creates a voltage across ZB, okay, and then it goes through, and it goes through ZA, okay, and then it comes back, okay, and then it goes back. Okay, similarly, there's another portion of the current, splitting of the current, okay, and then it flows through ZB, and then it flows through ZA and then goes through ZB and goes back. Okay, and let's measure voltage V1 from port 1. Okay, so what do we measure? We measure the voltage across ZA, and then we measure the voltage across ZB. Okay, I suppose that's clear. Okay, and that gives us the voltage. Okay, so we need not, so that will bring us back to terminal 2 of port 1. Okay, so it's very easy to see there, to see what is the voltage. Okay, so let's of course we know that the current is because the impedance are equal, I is going to split into equal halves because ZA and ZB are going to be in series for both the paths for the current. So what we have here, so now we see that I by 2 is going to flow through ZB. Okay, so when what is ZB? 2. Okay, and then we see that, okay, and so it creates a terminal, it creates a positive terminal on the upside of ZA. Okay, and now we have to look for what is going to happen on ZB. Okay, ZB we see that I2 which has split and passed through ZA is now going to flow through ZB. Okay, and so the direction is different, and the terminal is going to be that is on the left side of ZB is going to be positive, or the right side is going to be negative. So there is a difference in voltage. Okay, between the difference there's a difference in the signs of the two voltages. Okay, one is across I by 2 into ZA minus I by 2 into ZB. Okay, so what is ZA and ZB? So the difference between them is going to be J2 plus J2 minus 2 multiplied by 1 by 2 because I by 2. Okay, so I by 2 is going to come into the picture. Okay, so we are having we see that the answer wherein we get minus 1, okay, plus J is going to be more. It's going to be the only answer. Okay, available. Okay, so 10th problem. Here again, we are having a 2-port network, okay, and Y parameters are given as I1 is equal to Y11 E1 plus Y12 E2, and I2 is equal to Y22 E1 plus Y22 E2, okay, and it's shown appropriately that we are having a T network, but we want the Y parameters. Looks like we want the Y parameters. So what do you do with that? You just convert it into a the T network into a pi network, or the star into a delta. How do you convert the star into a delta? We see that we are having equal values, so 1/3 the value. Okay, so we are having twice the that is, yeah, we are having 3 times the value is going to be the equivalent for delta. But then we are working in terms of admittances, so take their reciprocals. So all the admittance values are going to be 1/6. Okay, the impedance values are going to be 3 times. Okay, and the admittance values are going to be 1/3 into 2, or 1/6. Okay, so now we can easily find out y11 is 1/6, 1/6. So it's 1/3, and only answer B seems to be correct. Okay, we'll just follow 3. So similarly, we see that so it should be 1/6 plus 1/6, 1/3 for both y1 and y12, and the single value of the top quantity is going to be 1/6 with a negative sign. Okay, so minus 1/6 more is going to be y12 and y21. Okay, problem number 11. We want to find out. It looks like a transistor circuit with all beta values and Re, collector resistance, emitter resistance, etc. given, but we want to find out the two-port network. So the circuit is something else, but we are expressing it in terms of Z parameters. This is exactly what I told you earlier. That is, what the circuit is not what is being conveyed. It is just an understanding or an interpretation or a representation which is being conveyed. Okay? So how do we find out Z11? What do? We set up a voltage V1, okay, and allow a current I1 to flow. Okay, I2 will be 0. Okay, and then we find out the mesh. We find out what is the voltage V1. Okay, so the voltage V1, if you give a I1, the I1 current goes back. Okay, nothing happens to the other part of the circuit, though we have a common reference at the bottom of the circuit. So Re is going to be Z11. Okay, but what we want is Z12 and Z21. Okay, so Z12. Okay, so Z12 means that you have to give what is called as you don't give I1, but you give I2. Okay, and then you measure the voltage V1. You see that you get nothing. Okay, so you say that it's equal to 0 because you are not giving any current. So if you measure V1, nothing happens. So we see that Z12 is equal to 0. But Z21 is not equal to Z12 because this is a nonlinear circuit. Okay, it's an active circuit. Okay, because there is a active element there. Okay, so that's the reason why when in active circuits you may not get these quantities as equal. Okay, so because it's not reciprocal. Okay, yeah. So now moving on to Z21. So what is Z21? Z21 is the same as equal to V2. Okay, divided by I1. Okay, V2 divided by I1. I2 is set as equal to 0. Okay, so we give V1, the I1 flows. Okay, and when I1 flows, we have beta I1 flowing, but there's no I2 as I mentioned earlier. So this beta I1 that we have that is flowing down, that because it's a dependent source, it's a dependent current source, though it's not shown that way. So this beta I1 now flows through R0. Okay, and creates a voltage as given by beta into R0. But the bottom terminal is negative. But we measure from the other side, so we see that V2 is equal to minus beta V0, and then divided by I1, you see that minus beta I1 R0 divided by I1 gives you minus beta R0. Okay, I suppose this is clear. Okay, if the concepts are clear, it's easy. Otherwise, it's a little tough. Okay, so moving on to the 12th problem. We are moving into little tougher problems because all of them are active. Okay, so here again we have a 10 E1 source right in the middle. We also have 2 ohms and 4 ohms, and we have E1 and E2, and these are the variables which we use to calculate the parameters. What are the parameters? As before, no, a little different. The Z parameters, Z11 and Z22 for the two-port networks we figure out. Okay, so what is Z11? Okay, Z11 is the same as equal to, I hope you remember, though the formula are written there. Okay, so we have called them E1, etc., but it's actually V1 by, our convention happens to be V1 by I1, where I2 is equal to 0. Okay, so if I2 is equal to 0, we see that this I1 current flows through 2 ohms, then it flows through 4 ohms, and then it flows to then it's 10 E1 as well, and now we can pick up all the voltages and call this equal to E1. Okay, so that's exactly what is done. That is, E1 is equal to, okay, we are having E1, that is the applied voltage is the same as equal to 2 into I1, okay, plus 4 into I1, or 2 plus 4 I1 minus 10 I1 because the direction is different. Okay, so we have minus 10 E1. So just put them all together, okay, and find out E1 by I1 or V1 by I1. So we see that Z1 is equal to 6 by 11. Okay, I hope it's very simply understood. Okay, very simple. Okay, if you have followed all the conventions. Okay, now we move on to the next context. We want to find out Z21. Okay, Z21. What does Z21 imply? It means that you measure V voltage V2. Okay, and you apply current I1. Okay, I2 is equal to 0. So I1 is applied. Okay, it flows through 2 ohms. It flows through 4 ohms, and it also enters 10 E1. And you measure from this side, that is from port 2 to get E2. Okay, but at the same time, since there is no current flow, right? Okay, no current flow from port 1 or I1 is equal to 0. Whatever voltage, that's the reason why we don't set E1 equal to 0. So E1 is the same as equal to, okay, because there is no there is no drop across 2 ohms. So if you look at the Kirchhoff's voltage law all through the circuit, it's clear that E1 minus 0 is equal to E2 or E1 equal to E2 because there is no current through 2 ohms because I1 is equal to 0. So no voltage drop. Okay, so this is something that we normally forget. So I hope you remember this. E1 is equal to E2. So if E1 is equal to E2, then it's very simple to find out that the voltage across 4 ohms and 10 E1. Okay, it's the same as which is measured as equal to E2. So E2 is the same as E2 by I1, which is equal to Z21 is the same as equal to 4 by 11. Very simple because we see that E2 is equal to 4 I1 minus 10 E1 and E1 is the same as equal to E2. Okay, so you just collect together all E1 and then equate it to 4 I1. So we see that Z21 is equal to 4 by 11. Okay, so of all the options, we see that B is perfectly right. Okay. So moving on to the 13th problem, the impedance parameters Z11, Z12. Okay, so these are similar problems, but of course they are twisting the whole picture by giving us a star and a delta together. Okay, so what do we need? We need the star. Why do we need a star? Because we are supposed to find out the Z parameters. Okay, so the delta within or the pi within we convert into the P. Okay, so what do we have here? We see that the pi within can be given by 1 into 2. 1 into 2 divided by 2 plus 1 plus 1, or in other words 0.5. Similarly, we have other legs as well, but we want to have only Z11 and Z12. So you need not find out the quantity which is going to be connected to 3 ohms at all. It's not required. Okay, so of course you can do it, but I have not put it here because it's not required. Okay, so Z11 will be the same as equal to 2 plus 0.5 plus 0.25. Okay, so 2.75. Okay, and what is going to be Z12? It's going to be what is going to be at the central limb. Okay, alone. Okay, not being assisted by both the sides. So that's equal to 0.25. Very simple. So long as the conventions are followed. Okay, so you do these problems very mechanically. Okay, not much of cons. Okay, of course, once the methodology is clear. Okay, so now we move on to another black box with Z parameters with 20 volt and 10 ohms on one side and ZL on the other side. Okay, and what is asked is the Z parameter of the two-port network shown in the figure are Z11, Z12, Z21 and Z22 are given as 40, 60, 80 and 100 ohms respectively. The average power delivered to RL equal to 20 ohms in watts is what. Okay, so yeah, so where do we start from? We start from V1. So what is V1? V1 is the same as equal to 20 minus 10 I1. I hope this is clear because I1 is being pumped into the the circuit which is represented with Z parameters. Okay, so V1 is equal to 20 minus 10 I1 is the same as equal to, yeah, we talk about the Z. Now we talk about in terms of Z parameters. What is that? Z11 which is 40 into I1 plus Z12 which is equal to 60 into I2. Okay, so we have an equation in I1 and I2 which is the same as equal to 40 I1 plus 60 I2 as equal to 20 minus I1. Collect them together such that 20 minus 50 I1 is equal to 60 I2. Okay, now we go to the other side. What is V2? V2 is equal to I2 into RL. And what is RL? RL is equal to 20 ohms. Okay, so we are having, and what is the direction of current has followed conventions. So the voltage V2 is now going to be going to have a change of sign. So I2 into RL or minus I2 into RL is going to be V2. Okay, so minus I2 into RL is equal to I2 is equal to 80 I1 plus 100 I2. Again, only two unknowns. Okay, because we have I1 and I2 are unknowns, but at the same time we are having two equations. Okay, so that gives us minus 120 I2 is equal to 80 I1. Okay, so you can find out the value of I1, the relation between I1 and I2. Okay, and substitute, and you can see that I2 is equal to minus 4 by 3. Okay, so if I2 is equal to minus 4 by 3, then the power delivered is going to be I2 square into RL, because the power is delivered to RL. Okay, so that gives us 35.5 watt. Okay, so you can do other things by just representing whatever is happening inside many components as a black box with using any of the parameters. Okay, so let's look at 15 problem. The Z parameter matrix for the two-port network shown is it's given as 2 j omega, j omega, j omega, and 3 plus 2 j omega, and the entries are in ohms. Suppose ZB is equal to RB plus j omega, and ZA and ZB and ZC are shown as a T network. So value of ZK. So we realize that ZA plus ZC is equal to 2 omega, 2 j omega. Okay, and what we are supposed to find out is RB. Okay, so ZB is in where does ZB come? ZB comes only in Z22, isn't it? ZB comes only in Z22, and what is Z2? Z22 is equal to ZB plus ZC. Okay, and where does ZC come? ZC comes only in Z12 and Z21. Okay, and they are shown as equal to j omega. Okay, so we see that j omega plus j omega plus RB plus j omega is going to give us Z22, and that's equal to 3 plus 2 j omega. So very easily we can see that RB is equal to is equal to 2, is equal to 3. Okay, so very simple. So let's move on to the 16th problem. Okay, a little too many problems, but of course they are simple. As also in this problem, because a two-port admittance circuit is asked, but we are given the impedances in a pi network. So automatically, okay, natural. The first thing that you are supposed to do is to go for the admittances. So 1 by 10, 1 by 10, 1 by 5. Okay, and then add together 1 by 10 and 1 by 5. Okay, so 1 by 5 is 0.2, 1 by 10 is 0.1, 0.3. Okay, similarly, same thing happens for Y22 as well. 0.1 plus 1 by 5 is 0.2, 0.3. Okay, and what is common is going to be 1 by 5. Okay, which is, and with a negative sign. Okay, so A is right. Okay, so as quickly you can do this. Okay, and then we again have for the two-port network shown in figure, the admittance matrices. Okay, so admittance matrix is shown after taking the admittance values. So 1 by 10, 1 by 10, 1 by 10, 0.1, and then adding together y11 and adding y1 and y2 together to get 0.2. Similarly, because they are all similar, we have 0.2 and 0.12 as y1 and y12, and minus 0.1 as y12 and 2. Okay. Yeah, so the last slide. Okay, again we are having E1, I1, E2, I2, 5, 20, 10. Different. Okay, they are all different. Okay, and we are supposed to find out the Y parameters. Okay, so there are several methods, but of course we can go for finding the 1 by 5 plus 1 by 20 as equal to, okay, what we require only y12. Okay, so we can find out, so we have 1 by 20 alone to be, subscribes to the answer, which is equal to minus 0.05 mho. Okay, the ohm reciprocal of ohm is mho. Okay, the last problem. This seems to be a little more interesting. The circuit shown below, the network N is described with the following Y matrix. Okay, 0.1 S, minus 0.01 S, 0.1 S, okay, Siemens, okay, and 0.1, because it's all, okay, either you call them either as mho or Siemens, and that's the alphabet S there. The voltage gain V2 by V1 is asked. Okay, so we need to find out many things. Okay, let's start off by understanding what is V1. As before, 100 minus I1 into 25 is going to be V1. And V2 is going to be minus 100. Okay, so the same concept that we borrow to this problem as well. So minus I2 into 100 is going to be V2. Okay, now we write out V1 and V2 in I1 and I2 in terms of the Y parameters. So what are the Y parameters? We see, okay, which are already given. So we see that 0.1 V1 minus 0.01 V2 is the same as equal to I1. Okay, and here you substitute for V1 as equal to 100 minus 25 I1. Okay, or you substitute for I1 as equal to I1 is equal to V1 by 100. V1 minus 100. No, you substitute for I1 is equal to 100 minus V1 by 25. Okay, so which is what is given there. Okay, so now rearranging, we see that 0.14 V1 minus 0.01 V2 is equal to 4. Okay, so easily you can you have a relationship between V1 and V2. Okay, so moving on to the next part of the Y parameter representation, we see that 0.V1, okay, the next row of Y, okay, 0.V1 minus 0.V1 plus 0.1 V2 is equal to I2. And what is I2? We know already I2 is equal to minus of V2 by 100. Minus V2 by 100. Okay, so now we just rearrange. Okay, now we have only V1 and V2 coming together, which is equal to 0.1 V1 plus 0.11 V2 is equal to 0. Okay, so there's a negative sign. And we see that the answer is going to be minus 1 by 11. Okay, so that's all. In this section, I will not do a lot of consolidation because essentially we follow the rules. Okay, there are 4 interpretations for any parameter. One is of course the fact that it is something like a black box wherein it is being represented using 4 variables. Okay, the input voltage, the output voltage, the input current and output current with conventional directions as shown. There are different kinds of parameters. In this section, we discuss mostly Z parameters and Y parameters. The second representation, the second understanding that you can have is that you give a voltage V1, okay, and then you observe what is happening. Okay, you can measure I1, you can measure V2, and you can measure I2, and you can connect between them in Z parameters or Y parameters. Okay, this is the second interpretation. Third interpretation happens to be that for Z parameters, you can always again re-represent the circuit as a T network. Okay, and then it's going to be Z1 plus Z2. Okay, Z1 plus Z2, I'm just showing the reaction. Z1 plus Z2 is Z11, Z3 plus Z2 is Z22, and whatever is in between, that is Z2, can be the Z12 and Z21. Okay, its dual happens to be the Y parameter. Okay, so what do we have here? You have a pi network for one thing. And then everything has to be in admittances. Okay, if everything is in admittances, we again see that, okay, there's a central element and there are 2 legs. Okay, so first leg Y1, central element Y2, the other one Y3. So Y1 plus Y2 is equal to Y11. Y2 plus Y3 is equal to Y22. And minus Y2 is going to be Y12 and Y21. Okay, as simple as that. The fourth interpretation is that because they are duals, okay, you get one of them. You get either Z parameters or you get Y parameters. Okay, and then what do? You simply take the inverse. You get the other because it's a 2 by 2 matrix in our case. These are some of the advantages. Of course, the best method or what is expected is always going to be the fact that when you are in Z parameters, you get Z1 by giving a voltage V1, dividing it by the consequent current I1, where I2 is equal to 0. Okay, now you replace each of these quantities, you get all of them. Okay, so the most important aspect that you had better remember is that V1 and V2 are given by Z11 I1 plus Z12 I2 and Z21 I1 and Z22 I2. Okay, so there all the setting to 0 etc. can be done for Z parameters. For Y parameters, accordingly, okay, or by extension is I1 is equal to Y11 V1 plus Y12 V2. And I2 is the same, is equal to Y21 V1 plus Y22 V2. I hope it's well understood and any problem can be done by you. Thank you.